Swayam Prabha. Digital India. Educated India.
Welcome to the third lesson of module 3, which is on thin walled pressure vessels, and we have looked into some aspects of thin walled pressure vessels in the last two modules or two last lessons in fact, and in this particular lesson we are going to look into some more aspects of thin walled pressure vessels. So this is on thin walled pressure vessels part 3, which is of course the application of stress and strain. Well, it is expected that once one goes through this particular lesson, should be able to understand the concept of volumetric strain in thin walled pressure vessels. Now, in the previous lessons we had looked into some aspects of cylindrical pressure vessels and spherical pressure vessels, that how the strains are generated when it is subjected to internal pressure. Now, because of changes in the strain or because of the change in the deformation, the cylindrical members or the spherical vessels, they undergo change in the volume. So we will like to evaluate that what is the strain in terms of the volume. So change in volume over the original volume, which we call as the volumetric strain. Now what is the value of those for different pressure vessels? Also one should be able to evaluate stresses and deformation in thin walled pressure vessels and appreciate the difficulties. Now we will look into some aspects, especially when we discuss about the combination of spherical and cylindrical vessels, that what are the problems related to the deformation and what are the aspects should be looked into when one should go for the detailed analysis or design of such vessels. Hence the scope of this particular lesson includes the recapitulation of previous lesson, which we do generally through the question answer session. We will look into the answers of the questions which I have posed last time, and thereby we will be able to recapitulate the aspects which we have discussed in the last lesson, and then we will be deriving the formulae for evaluating volumetric strain in thin walled pressure vessels, both cylindrical type and spherical type, and then we will be looking into some examples for evaluation of stresses, strains and deformations in thin walled pressure vessels, and these examples also will be related to cylindrical type of pressure vessels or spherical type of pressure vessels. Well, let us look into the questions which I had posed last time, and the first question was, what is the value of maximum strain in spherical vessels? Now in the last lesson we had discussed aspects of the spherical vessels, that if a spherical vessel is subjected to internal pressure, then how the deformation takes place, and consequently what are the stresses and strain that occurs in the spherical vessel. So now let us look into what is the value of the maximum strain. Now we had evaluated the values of the stresses, and if you remember, for a spherical system or a spherical vessel of this kind, the stress that exists is the sigma, both in the x and the y direction, and we had written down the resistive force, which is sigma times area, which is equals to twice pi r t, where r is the radius of the internal radius of the sphere or spherical vessel, and T is the thickness of this particular vessel, and the pressure that is being exerted by the content inside the container, this is capital P, which is equals to the pressure P times pi r square, and these two when we equate we get the value of the stress. So, this gives us the value of sigma as equals to P r by 2T, which we have evaluated last time. Now, this is the amount of stress. Now, this is being a spherical vessel. Now, wherever we take a section through the center, we get identical type of stresses, and hence the on this particular element we have both in the x direction and y direction the value of normal stress as sigma. Now, if we like to compute the strain, let us say based on this stress, if we like to compute the strain, now strain as we know, if we want to compute in the x direction, is equals to sigma x by E minus mu times sigma y by E. Now, here since sigma x and sigma y both are sigma, sigma x is equals to sigma y is equals to sigma. Hence, if we substitute over here, we get epsilon x as equals to sigma by E minus mu sigma by E, and this is equals to 1 minus mu divided by E times sigma. So, corresponding to the maximum value of the stress, which is equals to P r by 2T, we can compute the strain, and the strain let us call this as epsilon, which is as a function of stress sigma. So, this is the maximum strain that occurs in a spherical vessel. Now, the second question posed was, what is the value of in plane shear stress in spherical vessels? Now, if you remember last time we had discussed the in plane stress in a cylindrical pressure vessel, wherein we said that if you have the values of sigma x and sigma y as sigma 1 and sigma 2, sigma 1 was the circumferential stress and sigma 2 is the longitudinal stress. So, if we take these two stresses and compute the we can compute the strain, and also in terms of these stresses we can compute the in plane shear stress. Now, sigma 1 for cylindrical pressure vessel was P r by T, and sigma 2 was P r by twice T, and as we have seen in case of spherical vessel, sigma is equals to P r by twice T, and here both the values of sigma 1 and sigma 2, which was in the longitudinal direction in case of cylindrical member, in case of spherical vessel they are the same, and this is P r by twice T. Now, as we had seen in case of cylindrical vessel that the shear stress is sigma 1 minus sigma 2 by 2 is the maximum in plane shear stress. This is maximum in plane shear stress, and this is equals to sigma 1 minus sigma 2 by 2. Now, in this particular case, since both sigma 1 and sigma 2 are the same, or sigma x sigma y is sigma, hence the value of the in plane shear stress in case of spherical vessel is 0. So, in plane shear stress in case of spherical vessel is equals to 0. Now, third question was are the stresses same in spherical vessels as observed in cylindrical vessels. Now, this was the question which was posed in the previous lesson as well. Now, what you need to look into the derivations as we have done for both cylindrical vessels as well as the spherical vessels, and if we look into, we can immediately get an answer for what is the difference between the two. Now, in case of cylindrical vessels, if you remember that we have circumferential stress which is sigma 1 and sigma 1 times T times L for the length L of this element. This was equals to P times twice R times L, and from which we had calculated that this L gets cancelled. So, sigma is equals to, this is twice of this because you have this as well as this. So, this 2 also gets cancelled, is equals to P r by T, and consequently the longitudinal stress sigma 2 we had obtained as P r by twice T. Now, in case of spherical vessel, as we have seen right now, that we have only one stress which is equals to sigma, and that is equals to P r by twice T. Now, please note that in case of cylindrical vessel we have the circumferential stress which we have called as hoop stress as well. This is circumferential stress or the hoop stress, which is equals to P r by T, and the longitudinal stress is P r by 2T, which is half of this sigma. So, sigma 2, as we have seen in the last time, is equals to sigma 1 by 2, and the stress which we have in case of spherical vessel is equals to P r by twice T, which is again half of sigma. So, this is sigma 1 by 2. So, in case of the maximum normal stress which we get in case of cylindrical vessel, maximum normal stress is equals to sigma 1, which is P r by T, and maximum normal stress, this is for the cylindrical vessel, and for spherical we get maximum normal stress which is equals to P r by 2T. So, it is half of that, the maximum normal stress in case of spherical vessel is half of that of cylindrical vessel. Now, this aspect probably you can appreciate more through this particular diagram. Now, if we look into, say, this is the stress corresponding, this is the sigma 2, which is the longitudinal stress, this is an element which has been taken out from cylindrical vessel. Now, in case of cylindrical vessel, what happens is, along the longitudinal axis, the stress which exists really does not contribute to the equilibrium of the pressure which is being exerted on the curved surface by the content of the liquid. Now, only the stresses that resist the internal pressure is the circumferential stress, and hence the value is larger, whereas in case of spherical vessel, as it can be observed from this particular figure, here we get the stress from both directions. That means, the stress which is being exerted or the pressure which is being exerted by the content of the spherical vessel is being resisted by the vessel in all directions. Now, as we have seen in both the cases, both for cylindrical as well as the spherical vessel, the pressure which is exerted on the curved surface, they are the normal to the surface, and since the wall is thin, the variation of the stress across is negligibly small, and we disregard that, and hence we have a biaxial state of stress which is in terms of sigma 1 and sigma 2. Now, in case of cylindrical pressure vessel, this longitudinal stress does not really contribute much to the equilibrium of the curved surface, whereas in case of spherical vessels, the curved surface or the stresses from both directions comes in the resistance of the pressure which is being exerted by the content, and that is the reason the stress in case of cylindrical one is more than the spherical one, and in case of spherical vessel we have uniform tensile stress over the entire surface, which we normally call as the membrane stresses. Also, if we look into this particular aspects of it, this is to be noted that if we have a vessel which is a combination of cylindrical vessel and this is the cylindrical part, and the two ends we have the hemispherical part. So, this is spherical part, and this end as well we have the spherical part. Now, this is a combination of cylindrical and spherical vessel. Now, as we have seen that the stress in case of cylindrical one, which is P r by T, is larger than the stress corresponding to the spherical vessel, which is sigma, which is P r by twice T. And also, if we compute the deformation, we will find that the deformation in case of cylindrical one, which is given by this, let us call this as delta, is also larger than the deformation which is caused in the spherical part, if we call this as delta 1. Now, the problem arises at this particular junction, where the container is a combination of the end of the cylindrical part and the starting of the spherical part. Now, at this particular junction, as we can see that we have larger deformation from the cylindrical end, we have smaller deformation from the spherical end. So, as a result there is a mismatch in the deformation at that particular junction. Now, so far as the whole assembly is concerned, now there should be continuity of the element, and thereby there will be some other kind of stresses will be generated apart from the stresses that we are discussing over here. So, when we go for the design of such system, when we try to go for sizing of such system, one should be careful in selecting the sizes, and one should be concentrating on the type of stresses that gets induced at that particular junction, and accordingly the thickness has to be decided. Now, at this point of time we are not going into the detail of that, only I am just trying to highlight the problem that can arise in case of such pressure vessels, where you have the combinations of cylindrical and the spherical one. But for the time being we assume that geometrically there will be smoothness, and we will have similar kind of pressure exist, and the corresponding deformation we can evaluate directly without considering the change in other kinds of stresses. Well, now having looked into this, now as I said that when you have liquid inside the container, whether it is a cylindrical vessel or spherical vessel, now as we have seen through the examples in the last two lessons, that it undergoes change in the diameter, thereby it undergoes change in the volume of the container. Now, if a volume of cylindrical or spherical vessels undergoes changes, then we should be in a position to compute that what are the changes in the volume. Now, as we have defined strain in case of a linear element, that extension to the original length is the strain, the ratio of the extension or the deformation to the original length is the deformation. Now, in case of volume change, we define that the change in the volume to the original volume as the volumetric strain. Now, we will be looking into that what will be the how we are going to evaluate the volumetric strain in case of cylindrical or spherical vessels. Now, let us look into the evaluation of volumetric strain for cylindrical vessel. Now, the value of the volumetric strain E, which last time if you remember we had defined delta V by V when we had computed the value of the bulk modulus, and we had designated that as E. We can evaluate this volumetric strain as a function of the pressure, the radius of the vessel, and thickness of the vessel, and correspondingly the values of materials which are E and mu. Now, let us look into the evaluation of this volumetric strain. Now, if we consider a cylinder, having length L and radius R, let us say the internal radius is equals to R and length is L. Now, after deformation, let us say the change is R plus delta R in the radius, and L plus, consequently L plus delta L is the change in the length after the content has exerted pressure and the dimensions have undergone changes in terms of the deformation. Now, if these are the changes, then the volume of the cylinder delta V by V is equals to, this is pi R plus delta R square times L plus delta L, this is the change volume, minus pi R square L is the original volume divided by pi R square L. So, this is the final volume after the deformation has occurred minus the initial volume divided by the initial volume. So, this is E, which is del V by V. So, this is equals to, if you take out pi from here, we have if we expand this R plus delta R square,